Okay, so we're going to launch into a problem, and we're going to look at how can I solve this. So what I have here are two terms. I don't have a trinomial, and the factoring strategy we've been talking about deals with a trinomial. So what I want to show you is how to change binomials like this into trinomials, okay? Now, I know it's missing the middle term because I have two different variables. And so the middle term would have the mixture of the square roots of those two variables. So I'm missing a term that has an HA. So what I'm going to do is rewrite this, and I'm going to put that missing term in. And I'm just going to call it plus 0 HA. Minus 9a squared. And then I'm going to play the game. And let's see, I have 16 times negative 9, so it's going to give me 54. And then I add a 5, so I get negative 144. And the sum number is this 0. So I need to think of factors that multiply to give me negative 144, but add to give me, that looks like 744. Let's clear that up. Sorry about that. I know. I say it, but it doesn't always look like it. There we go. So let me go back. So what are two factors that multiply to give me negative 144, but add to give me 0? So I do know that the signs are going to be different. Okay, so now before you guys give me your answers, what types of numbers are going to meet this type of condition? Natalie? Okay, square roots. So the numbers need to be the same number, right? Otherwise, I can't add opposites and get something else. I can't add non-opposites and get 0. So what am I going to write here for my two values, Natalie?
12,
positive 12 and negative 12. All right, so now we're going to turn my binomial into a 4-term polynomial using these two terms. So I'm going to put the negative one in the middle and then the positive one. And then I'm going to factor by grouping. So the first two have a 4h in common, which leaves behind a 4h minus 3a. And then the next two have a positive 3a in common. And that gives me a 4h minus a 3a. So I do have the miracle occur where they both have the common binomial of 4h minus 3a, and then I form a binomial from the coefficients. So I get 4h plus 3a. So I want you to look at the number we started with, or the polynomial, the binomial in this case that we started with, the 16h squared minus 16 or 9a squared. And I want you to look at the answer we ended up with, and I want you to ask yourself, when have you seen something like this before? Just looking at the two circled in orange. Morgan?
well, you can square the bottom and get the top.
Okay, so she's saying if I square this term and square this term and put a minus in between, it gives me that. Oh, sorry, I say minus and I write plus, sorry. It's just so instinctive for me. What is this called?
Perfect square.
It's not perfect square trinomial because it's not a trinomial. It's not called squaring binomials because we're not squaring a binomial. Squaring a binomial gives me a perfect square trinomial. Okay? Patrick? Okay, that's true. That's what factoring is. What we started with has a name. Beyond that, it's a very special binomial. Pardon me? No? Oh, ladies and gentlemen, you make me so sad. This actually came back from lesson in the beginning. Let's see, which one was it? It wasn't 8.2, was it 8.4 or 8.3? Multiplying polynomials. I think it was lesson, yep, 8.4. Lesson 8.4 talked about special products. The two special products it talked about is when you multiply a binomial by itself, you get a perfect square trinomial. And the second one said if you multiply two binomials where they are the same terms but opposite signs, the answer you get is a binomial that is the difference of two squares. And that's the name of this answer that we started with. And remember I told you, hey, you know, if you don't memorize this, you can still get the product answer doing it the old way. You know, you can either do distribution, you can do column multiplication, you can do the matrix. However, I said where it's going to cause you problems is we get to the second half of the chapter when we're going to be factoring. So that's where we're at right now. This special product combines with lesson 8.8, and what it does is if you recognize that you have a difference of squares, then you actually have a pattern you can use to get to the answer. But again, this I told you this is going to cause you problems. So basically what I just modeled for you is if you don't understand this pattern, that's how you solve a binomial, is you give it a zero middle term. And the zero is going to be your sum number, and then you go from there. Okay? So let's pretend that we all recognized what we started with. And so I'm going to show you how easy this is. So today's date's this. So again, if you don't get the pattern, I've given you a backup plan. All right? You can always factor playing the game, where zero, though, has to be your sum number when there is no middle term given to you. Okay? Now, this is where it gets a little tricky, because it has to meet certain conditions. So, conditions that must be met. For this pattern, for using the following pattern. If these conditions are not met, you cannot use this pattern. Okay, please understand that. This is only allowed with these conditions. So, condition 1 must be a binomial. That's condition 1. If it's not a binomial, you cannot even think about this, you throw it out. 2 must be a difference. If there's not a subtraction sign in your binomial, you cannot use the pattern that we're going to share with you. Okay? Next. Both terms must be perfect squares. That means if there's a coefficient, it's a perfect square. If it's a variable, it's a perfect square. So let's kind of outline that. So perfect square, coefficient. So those are all the result of multiplying a number by itself. So 4, 9, 16, 25, 36, so on and so forth. And what tells you that a variable is a perfect square? What about the exponent? Nope. Doesn't have to be a 2. Has to be what? Has to be an even. So exponent on the variable must be even. Okay? So these are the conditions we need in order for using the pattern I'm going to show you, or we're going to kind of work through together. All right? So everybody good here? Here, I'm going to put this. All right. So let's go back and let's look at just what we started with in that original problem and what we ended with. So we started with, so I'm going to call this, let's give it a title, the pattern. We started with, what was it, 16h squared, minus 9a squared, right? And we ended with, factoring it, 4h minus 3a times 4h plus 3a. Okay? So we look at our binomial. Does it have a difference?
Yeah.
Is 16h squared a perfect square?
Yeah.
Is 9a squared a perfect square?
Yeah.
So what this tells me is I have the difference of squares. So now what I have to think about is when we did lesson 8.4, what did the two binomials look like that ended with me getting this difference of squares? So my question is, how do I go from this 16h squared to this 4h? And how do I go from 9a squared to 3a's? So what's happening? Now remember, when we were doing this lesson, we started with the two binomials and we distributed to get to the answer. So this whole second half of the chapter is going the other direction. It's giving you the answer and your job is to go back to the binomials. So what's that called? What are we doing? What's the process when we go from an answer, an answer to the binomials? What's that called altogether? What's it called?
Factoring.
It's called factoring. Okay, so when we're factoring, how can I get 16a squared, or h squared, to become 4h?
Divide.
What do I divide 16h squared by to give me 4a?
4.
So could you agree
Is that
that 4h times 4h gives me 16h squared?
yeah.
Is there something I could do to 16h squared other than dividing that would give me 4h? I can do a square root. I can use a radical. So when I'm taking the square root of a monomial, we're taking the square root of the coefficient. Everybody should be writing this down. And we're taking the square root of the variable. What's the square root of 16?
4.
What's the square root of h squared? Okay, what am I doing with the exponent when I'm taking a square root? I went from 2 to 1. No thoughts? Okay, do it this way. Let's take this and let's rewrite this using a fractional exponent. How do I write square root using a fractional exponent? 1/2. Now, when I raise a power to a power, what do I do with the exponents? I multiply. What's 2 times 1/2?
1.
Okay, now, I'm going to ask my question again. What do I do to an exponent when I take a square root? You take it to the half power. You multiply it by 1/2. You cut it in half. All right, so let's just explore this for a moment because I see this is a troublesome spot. So let's make it a bigger number. Let's make it h to the 28th power. Okay, so if I want to take the square root of that, And square root just simply says raised to the half power. And raising a power to a power simply means to multiply the exponents. I get h to the 14th power. This is why it's so important to understand that flexibility between a radical and a fractional exponent, because now you can understand when I say to take the square root of a variable, you take half of the exponent, because that's what square root means, is take it to the half power. Okay? All right. So, does the same pattern work on the 9? If I have 9a squared and I want to take the square root of it, I'm going to take the square root of 9, and I'm going to take the square root of a squared. What's the square root of 9? 3. And what's half of a squared? A. Okay? So, basically, my pattern is very simple. Once I recognize I have a difference of squares, all I'm going to do is take the square root of the two terms. Okay? So I'm going to do this on the next page. I've cluttered up this whole page. Everybody good here? Yeah? Okay. So let's go back and I'll title it again, The Pattern. First and foremost, yes, it's the difference of squares. Wah. 2. Take the square root of the first term. This becomes the first term in the two binomials that form. Three. Take square root of the second term. This becomes the second term in the two binomials formed, or that form. Make one binomial a sum. So you're going to put a plus sign there. And one binomial a difference. That's a minus sign. And now you have your two factors. Okay. Johnny Ray, I don't see you writing. All right, here we go. Ready? So we're going to do some problems, but I'm going to tell you right now, I'm going to mess with your minds. Ready?
What's the square root?
Okay, guys. So let's do some practice, and I'm going to give you all kinds of problems. So the directions are going to say solve. Now, here's what's going to be challenging, is that you guys are going to see binomials on a test, and if it isn't a difference of squares, then in your mind you're going to say it's prime. But the reality is, number one is you got to look for GCMF, right? So anytime we factor, you got to look for GCMF. And then you got to look what's left behind. And if that binomial is a difference of squares, then you're going to use this process. But they don't stop there. So I'm going to give you all sorts of different examples. Okay, so let's start with this one. Or it'll say factor, not solve. Solve means there's an equal sign, so they'll tell you to factor. So we're just going to focus on this day. So we get 27 g cubed minus 3g. So first glance, if I'm not thinking, I'm going to say this isn't the difference of squares. 27 is not a perfect square. G cubed is not a perfect square. It's an odd exponent. And that's when you have to stop yourself and say, whoop, can I pull out a GCMF? Is there GCMF? Okay, not just a 3. Not negatives.
3G.
We have a 3 and a G. Then we factor and we end up with a 9G squared minus 1. So now I look at the binomial, the remainder, and ask, is that the difference of squares? And the answer is yes, it is. So out in front is the 3G. Then because I've said yes, I know I'm going to get 2 binomials. I know that one's going to be sum, one is going to be different. So I can put in that frame. And now I get down to business. What's the square root of 9G squared? 3G. That goes in the front because 9G squared was in front. What is the square root of 1? 1. That goes in the back, and I'm done. Okay? Now, I'm going to throw a couple of ugly ones at you and make sure that we get this down. So, sometimes we're going to end up with a GCMF that we have to factor out. So that was an example of that. All right, let's do one that's more like the first one. 64G squared minus H squared. So, is there GCMF? GCMF?
No.
No. There's no coefficient, and the variables aren't the same, so I can't do anything. So then I ask, is it the difference of squares? Does it meet the criteria?
Yeah.
It's a difference, perfect square, perfect square. So I make my frames, 2 binomials, one sum, one difference, and by the way, it doesn't matter who's the sum and who's the difference, so I'm going to do it the opposite this time. First one, what's the square root of 64G squared? 8G. That goes in the front of both binomials. What's the square root of H squared? H. And I'm done. Okay, so now to mess with your mind is the next one. B squared minus 16. GCMF?
Yes. No.
No coefficient, that's the same, and only the first guy has a variable. Perfect squares? Difference of squares? Yeah, meets the criteria. So I get my frame in. Oops, one sum, one difference. And I'm going to tell you that my preference is that you put the minus in the back. And you'll see why in just a second. So let's take the square root. What's the square root of b to the 4th? B squared. And then what is the square root of 16? And I'm going to tell you, you're not done. The problem with difference of squares is that sometimes when we do the difference of squares and factor it, we create another factor that is also the difference of squares. So every time we factor the difference of squares, we need to check out the difference binomial and see if it meets the conditions. So it's a binomial, it's got subtraction. Is b squared a perfect square?
Yes.
Is 4 a perfect square? Yes. So what happens is I'm going to still have b squared plus 4 because I can't do anything with him, but now I'm going to create 2 new binomials, one sum, one difference. So I always put my minus in the back because I look at the last thing. That's where my eye always trails to the last thing. Now for some of you, you want to put it in the front. It's up to you to decide what pattern works best for you, but you have to constantly ask yourself the question, is that binomial that I got now also a difference of squares? Okay, so if the answer is yes, you have to keep going. So what's the square root of b squared? So I have b's in front. What is the square root of 4? 2. The only place I look is at the last one. Is that the difference of squares? B has an odd exponent, so I know I'm done. So this is your final answer. So you have to watch out for this. And it can go on forever, especially if you have a number that has lots of perfect square factors. So it can go on for a while. Yes?
And so when you have the b squared plus 4, you always take the positive, not the negative? Or does that matter?
What do you mean?
Because you know how you have the b squared plus 4 and
Uh-huh.
the b squared minus 4?
Uh-huh.
Can I take the b squared minus 4 instead of b squared plus 4, or is it always a positive one that you take?
The one that I keep or the one that I factor again?
The one that I keep into the trinomial.
Okay, the one that I always keep is going to be the positive one because there is no rule for factoring the sum of squares. I only have one for difference of squares.
Okay.
All right, so that's what your homework is going to be practicing, but they're going to have a mixture of things on there today, so don't think it's all going to be this, or it may not look like anything until you factor the first round and you realize, oh my gosh, there's more to do, okay?